in 1980. And what happened with the Walkman? It was the first time where the audio modality comes out of our door and it went with our body around because of this heavy phones. One of the big issues there was that since of the portability, then one of the first implications in technology is that I cannot have all the LP OCDs in my room, but they should be portable. Then discs or cassettes, and then iPod and other technologies. So also bringing the information with you is very, very important. Now this is for the audio modality. For the visual modality, I know probably you heard about this new project started actually also by a colleague of us in robotics with Google, and the project is Google Glasses that brings the idea of wearability with visual modality. In particular, wearability, this is, for instance, the first case where wearability makes a sense for me. Because the wearability in Google Glasses means that your eyes should be free to see in front of you and should be busy only if some information occurs. So it's not the classical helmet which stops you looking outside. I mean, looking with your eyes. So the idea of Wear Up is to bring this concept of portability for haptics. So touch is missed here. And we know that for touch we have several devices, like commercial devices, experimental devices, but most of them are grounded. So you cannot bring around. Okay, you can bring around something, but it's something like exoskeleton, very, very heavy and not really extremely wearable. Okay, so we are imagining several applications with Wear Up. Wear Up is more, is not focused on a special application, but is more general. We want to study the methodological and the technological background of this wearable haptics, and we are imagining several applications. And the some ones are the ones that we focus more within the project. Is human-robot cooperation, advanced teleoperation, especially the ones that are developing Pisa and IIT, also healthcare and gaming and virtual reality. Okay, the concept of wearability is something, of course, very interesting. But the new in the concept of human-robot interaction, the new thing that we can say for humans is that we cannot only read what is the human posture, understand what is the human posture, but we can also write on the human body with forces. So we can command something with forces. So the idea is to use this new paradigm. Now, the concept of wearability is designed in this picture. So we are imagining something on the arm and on the hand, which does not stop you doing something like holding an iPad, drinking some coffee, and writing with a pen. So it should not stop the use of this device, the ability to do something like the things that are shown here. Okay. I will skip this slide and I will go to the main slide of this first part. This is, I mean, in my opinion, is very very important. As you can see there in the first image on the left, you can see the standard haptic device, like the kinematic chain of the Phantom, applying forces on your fingertip. Okay, so the idea is to apply forces on your fingertip to simulate something. This is, of course, the A figure is not wearable at all because it's grounded, so you have a limited workspace. Then what you can do, you can wear those devices on your arm, and you can put the ground on the shoulder, or on the arm somewhere, and you have an exoskeleton. And the exoskeleton comes with you, okay? But then you have those structures like the mechanics around the hand, which is of course wearable, but it's not wearable to the extent that we want. To bring wearability to the level that we want within Wear Up, you can see from design B to design C is to remove the exoskeleton. If you want to remove the exoskeleton, you have to move the base where you ground the exoskeleton towards the point where you want to apply the force. So if I can use Usama, I mean, you do the human, I do the robot, so I have the haptic interface. Can I use your finger? So this is the standard haptic, the Phantom, okay? This is the exoskeleton. Okay, of course you feel both this force and this force. So I have to enlarge the base, and can apply the force. Or I can go wearable. If I go extremely wearable, the device is like this. Okay? So what happens here? Here I remove all the exoskeleton, but there is a huge difference. The difference between B and C is that with C you remove the kinesthetic part, but you are only the spontaneous part of the body, which changes a lot the approach to us. This is where we want to investigate on it. This is the first device that we are designing at the cutaneous level, and here I have to say a big difference between typical cutaneous devices in haptics and the wearable one that we are designing. Typical cutaneous devices are used like pin array or maybe typically pin array, so matrix stuff, not applying forces. If you look at this device, and if you remember how the omega by force dimension is designed, the omega is designed in this way. There are three motors, a parallel structure, and a ball where you can grasp and you can apply forces on your fingertip. Take the omega. Imagine to have a large fingertip, put the fingertip in the middle, and let the ball applying forces on your palm, on your finger palm. So you have practically a parallel structure with the three motors on the nail and the platform moving on the fingertip, applying three directional forces on the fingertip. So you have a parallel robot, you can see the cables here steering that platform on the fingertip, and you can steer, you can do normal forces and tangential forces orienting the platform. The green part are force sensors because you can control this device both in position and force control in order to not calibrate human subject by subject, and that is the CAD design of the system. Here you can see an experiment where we were testing. This was the very first prototype. You can see the orientation of the platform applying forces according to how the ball moves along that surface. So you can simulate the surface. Okay, so you're able to apply forces on your fingertip. This is also a nice picture that they found in a journal. This was like the iPad if it was designed in 1935. What I want to say is that we can go wearable with haptics now because there is technology to do that. Because there are micromotors, there are sensors at the micro scale level that we can use because of wearability. This was not possible at a time where Phantom was patented at all, because there was no technology to do that. Okay, now another big part, of course, there is a good interconnection between robotics and neuroscience. In particular, robotics is very important. I will come to robotics in a moment, but the neuroscience part is also very important, because you are missing the kinesthetic part, which is the perception of the touch due to the muscles and tendons typically. Since you are stimulating only the cutaneous part, you are not applying forces, you are not using your muscles, which is indeed good for the teleoperation loop, also in teleoperation, because you are not inserting energy into the system. So, cutaneous part without kinesthesia means that you need to study neuroscience, psychophysics, to see to which extent you can reduce that part. And the robotic foundation we're up is, of course, is a multi-degree of freedom. We are not thinking to a single finger, but we are thinking to the whole arm. You can imagine the fingertips. You can imagine to recover some kinesthesia at the elbow level, because probably you don't want to reduce all the kinesthetic part, but you need also some muscle activation using a single joint system, like one that IIT is designing for the elbow or for the shoulder. And also this new, you can see the net, and this is an idea of Vincent Hayward and Edin Benoni that they are having. I will come back in a moment. If you see the two, if you want to see what are the main principles of neuroscience that can be used in wearable, I would have to mention one result by Vincent Hayward, which is a partner of this project, where he simply says that if you want to explore a surface like this, like a bump, then you both have force stimulation, and you also have some some motion of the finger around the corners. if you remove the motion and if you only apply the forces, then you still perceive the bump, which is very important for the cutaneous device that we are developing, because for the cutaneous device, you can only apply forces on the finger part. So you can feel some bumps, even if you do not have some motor pushing your finger in that direction. So this is a basic principle of wearability. Another basic principle developed by, discovered many years ago by Johansson and Edin, Ben is a partner of the project, is that the kinesthetic, when you move the finger, of course you are using the muscles and the tendons, but you also feel the motion, because there is some receptor in the hairy skin that perceive this kind of motion. So what they are saying is that what we're saying within the project, okay, but why don't we put something on the skin to stretch the hairy part and to let human feeling the kinesthesia? And this is something that we are developing. Another part that we recently published in 2011 is, okay, look, if you want to skip, instead of having all the robots at your fingertips, why don't you use the cutaneous part of the fingertips and only one single kinesthetic point? So if you have one single, I will show you the video. In this video, the experiment, you can see Stefano Scheggi, which is indeed here, where he's perceiving cutaneously on the fingertips something, and there is the omega, there is the kinesthetic part on the elbow only. So you have one kinesthetic point for the whole arm, and you can recover for some information only using that robot. We did some experiment. We tested the J&D with the cutaneous and the kinesthetic part, and we saw that the combination of both is really, really interesting. In particular, the kinesthetic, the cutaneous part was able to feel very light weights under the 300 grams. For larger weights, it entered the kinesthetic part. So our idea in Wearability is to use tactile and finger stimulation for lightweight perception and stimulation, and partial kinesthesia with the elbow, for instance, to recover the more heavy part. Now, one big thing in wearable haptics is tracking. Because for grounded haptics, the tracking of the body was for free. Because I'm connected to the kinematic chain, the encoder gives me the position. For wearability is a problem, because there are two approaches. One is to use, of course, accelerometers and IMU on top of this device, and then try to integrate, or you can use some external camera, like the Kinect in this case. In the project, there is Antonis Archilos from Fort developing some tracking of human hand. You can see a Kinect tracking. This is a work that we published in 2011, where you can see there is this scaling part. You can see larger motion here because the workspace is scaled. The Kinect is following human hand, and then the cutaneous device, the wearable haptics device, is able to apply forces according to what you feel in a wearable way. Now, let me back to the application of human and robots. So what we can do with this kind of wearable technologies. Okay, there are many things that we can do in several applications, like human-human communication, medical applications, and other fields. But I want to talk about two examples of using this wearable stuff in human-robot interaction and cooperation. We were using in our community, we were used to study team of robots, like leader follower formation, team coordination, and it was always almost difficult to put the human inside this team, because you can read the human probably through a Kinect, but it's difficult to say to a human, go straight, go right, go on left, or maybe to feel something on the from the robot. So our idea is to use this wearable devices to let a human be able to be part of a team. Now, the goal of this work is to have, so there are two mononomic robots following a human. The human is the leader in this case, and the robot formation is given by a certain distance in the center of the robot and the human, and a certain heating angle. Okay, the angle between the direction of motion and where I see the leader. There has been studies that says that indeed also the human motion is mononomic. In particular, Lamond and Bertels and others studied that to go from a point to another, humans behave like an autonomic kinematics. So we are in the same, let's say, framework, because the leader is an autonomic, has an autonomic behavior, and also the mobile robots following are autonomic as well. So we can keep going and use some results to let the robot following the human. So what was the problem here? The problem is shown in this picture. Suppose that human is and the robot is the follower. And suppose that the robot has some constraints, like non-autonomic constraints. The constraints on the follower imposes some constraint on the leader. So, for instance, if the follower has a limit on the maximum velocity, the human cannot run too fast. Otherwise, the team destroys, because there is a larger distance between them. So, how can I don't want the human turning his head each time to check if the robots are following, okay? So I want to use some haptic feedback to provide the ability of the robot to be able to follow the leader in some way. So I want the follower transmitting the constraints violation of the non-autonomy using this wearable technology. And of course, in this case, you can see that if you are safe, if you satisfy the constraint, that you can see the leader. Actually, the leader is a triangle here, is the blue one, and the robot goes in following easily the leader. And this was a work that we did a few years ago with colleagues from Parma. If you change and if you do some strange motion with the leader, like you have a reduced circle, of course, the constraints on the following robots, on the curvature in this case and non-autonomy, do not allow to follow. You can see very strange behavior. You have to turn back and go forward. So it's very, very, very strange. So you have to avoid this. How to avoid this? Okay, you can avoid this. So constraints on the mobile robot following imposes constraints on the human. And these are the constraints on humans, and you can feel, I mean, these are all the details on the constraints. Then you can build some band within, if you are inside this safety band, you start alerting the human with the haptic feedback. And you can see that using the haptic feedback, the human is able to satisfy the constraints for the formation to be, for the team to be in formation. And without the haptic feedback, you don't know what is going there, and you destroy the formation. So these are the details on the wearable stuff. These are the details on the wearable stuff. I don't want to keep you on this. These are the details on we activate the feedback. These are the details how we estimate from the robots the position of the human using the Kinect. And this is some experiment I want to show. This is some real experiments. You can see that without, on the left, without the feedback, the errors along the two axes grows, does not go around zero. With feedback, you can see that the errors, when the error is zero, it means that you are in team. Then on these two subjects, everything is okay, and you can see the activation of the haptic feedback. But just to give you a flavor of the experiment, see what happens here. Now Stefano is not using the haptic feedback, and he runs too fast, and it destroys the formation. Now he's using the haptic feedback, and as soon as he's running too much, they send an alert, so please stop, go slowly, and the formation is kept. If you see the curvilinear trajectory, you can see the same. In this case, it turns on the left too much, and you can see, if you look at the distance that increases, you destroy the formation. With the haptic feedback, you can see that while it turns, so he does not know what's happening on the followers, but he only knows through the wearable haptic feedback there. So this is very interesting, and of course there are things says that without the red one, without haptic feedbacks, the errors is much larger than without feedback, of course. with many subjects, many experiments, and things like that. This is a very new thing that we were doing with Antonio Franchi in Max Planck, and this is also where we met at FSS. And the idea is to use the wearable stuff, the human hand, to drive also different team of robots, like the operation of quadruptors. The operation of quadruptors is really interesting. The idea is that each quadruptor establishes one single contact point with the object. And then it's like having a hand, a flying hand, independent. So each finger has an independent control, so it's not centralized anymore. But we can use still the same concept of soft grasp that we are using in robotics. So the idea is that there is the human. Human has a free hand in this case. It moves the hand. Then there is the hand tracking, and there is a mapping. So how I can connect the motion of the human hand to a team of the robot? How I can show that this means grasping and this means moving, even if there is not a robotic hand anthropomorphic on the other side. And we use the results that we obtained in the End Embodied project, which is the mapping strategies, which is this. So the idea is to build a virtual object around some reference contact point. And so you have is to do a mapping in the object space. Instead of mapping the velocity at the fingertips, the velocity at the joint, you map the FX on the robot action, human action on the object that you are manipulating. But which object? Because this is general. The object is a virtual object, is a virtual sphere, it can be an ellipsoid around some reference point. And then what you control? You control the change of the radius, the rate of change of the radius, which is an information about the squeezing force. How squeezing you want, what is the internal force there? So the change of the radius that you map on the other side is the internal force that you want to do, and the other thing is the motion of the object, which is the velocity of the reference frame centered in this virtual sphere. So you have the reference point on the left, the reference point on the right. You build this virtual sphere like the minimum volume sphere, and then you simply command the same rate of change of the radius and the same velocity, linear and angular, of the reference frame. And you get, we published this in a robotic framework where the goal was to map the human hand with the synergies on a very different kinematic chain that is impressed on transaction robotics. And exactly the same framework now is applied in this experimental setup with CUC against Stefan, which is our subject, where there is the human hand tracked with the Kinect, and on the left you can see the track of human hand, and then human hand is mapped on the quadrotor on the simulation environment. You can see the video here. There is the human hand tracked. The Kinect tracks the human hand, and then the action on this virtual object is mapped on the action of these robots that go there and with compliance grasp an object and move the object on the other side. As you can see here, there is no force feedback, but for sure, using our wearable stuff, we can use the force feedback. And this is a paper that has been accepted that we will publish in IROS, where as we designed a forward mapping, now we are imagining a backward mapping from the grasped scenario to the single part of the finger that you have on the human hand. This ends my presentation. I have to thank all the people in my group, and most of them are here, and also the 3 projects we are running which deal with this subject, which is Grant, the End Embodied, and DALI, where there is the human robot operation.